Okay, here we go then. We are in Chapter 10, Lesson 2 on similar figures. You'll see the picture there on this first slide. Kind of explains the idea. Question is, what makes two figures similar? Well, it looks like from this picture, if they have the same kind of a shape, but they're different sizes. We're going to see that today. And we're going to ask the question, what is true about the corresponding parts of similar triangles? You remember with congruent triangles, the corresponding parts were equal. But here you notice the corresponding parts, like the bottom of these two, they're definitely not equal. But is there something that is true about their relationship to each other? Well, this first picture that we're looking at here is a picture of a movie, as seen on two different size screens. You see the top one is the now popular 16:9 ratio. This bottom one has a ratio length to width of 12:9. We often see it this way and this way, 12:9, but that's not familiar. This is normally what we'll see as 4:3. So these are the two main screen sizes. One thing that you'll notice on the 4:3 screen size, we miss things. We miss the sides. Movies are made in a 16:9 format, but TVs back in the day were 4:3. So a lot of times we'd be missing parts of the movie, and I think the movie makers tried to avoid putting anything crucial there. Over time, however, we started to develop ways to try to accommodate that. So here's a pan and scan. Again, you'll notice you missing things on the side. Here's a letterbox. They would take a 4:3 screen and they'd shrink it down so the width would fit there, but you'll notice then you'd get black on the top and bottom of the screen. Here's a small wristwatch size image. Of these images, these 5, which screenshots would you say look alike? It's a good question. So if you had to choose two, did you end up thinking that those two looked alike? They get about the same amount of screen on. Take a quick look at this. These are different size TVs. Here's 55-inch TVs. Looks like they're all 55-inch screens. But some of them are in a 16:9 format, this middle column, and then some are in 4:3 format, and you see that it looks different. This would be a full screen 4:3, but again, you'd be missing some of the video. Here's a 16:9 and a 4:3 letterbox where you lose some there. Same thing up here. It's another example of a TV screen, movie screen 4:3, 4:3 ratio. Then you see the 16:9, and again, you see that you miss some things. Well, what would happen if you were just to drag the dimensions? Well, here's a screen with the correct ratio. But if you just drag the dimensions in the wrong way, you see what happens. The aspect ratio gets messed up. Over here it was 4:3, and then over here they dragged it to a ratio that was not 4:3, and so things don't look right. Another example of some screen sizes. Here's a 640 by 480 screen size, and then two other screen sizes here. Are they similar? I mean, are they in the same ratio? Well, it's hard to tell with those big numbers, but if you put them in the fraction form and then divide them out to get a decimal for the ratio, you can see, yes, those first two, yeah, all three of them are actually in the same ratio. Dividing them out shows us that. So another set of screens. Now these don't look similar. I mean, if you look at these again, they look like they're the same size or same general shape. But these don't quite look that way. Dividing them out shows that they aren't. They're very close. That isn't much difference there. So what does this have to do with anything? Well, have you ever tried to change the resolution on your computer screen? You can do that. You know, you can go to the settings button on your computer and look at the screen display. This one's 1920 by 1080. That's 1900 pixels in one direction and 1080 pixels in the other direction. You can click on the drop down, and doing that would get you something that looked like this. Oh my land, look at all of the different choices. Which one should you pick? Well, if you just randomly pick one, you may end up with a distorted image on your screen. So you want to be careful about that. How would you decide which one to actually pick? Well, what you'd have to do is you'd find the ratio of these two, 1920 divided by 1080. Remember that decimal, write it down. And then do the math on some of these other ones and find one that has the same decimal ratio. So here we are again with these two images from our first slide earlier in the show. We would say that these two rectangles are similar. Now, why is that? What seems to be true about the corresponding parts in these two images? In other words, if we were to compare the length of this one to the length of this one in a ratio, and then the width of this one to the width of that one in a ratio, what do you think might be true? Maybe the ratio is the same? We'll get back to that in a minute. These two triangles are similar. And if they are, we say their corresponding sides are proportional. That's going to be the tricky part to understand. The corresponding angles are equal. That one's a little bit easier to understand. In other words, angle A corresponds to angle A prime, and those two angles are equal. The same with B and B prime and C and C prime. So the angle part is easy. What about the sides? Well, AB, this segment, compared to A prime B prime, that'll give us a ratio. You do the same with the other corresponding sides, and you'll find out that the ratio is going to be the same in similar triangles. So back to this picture. If you had to estimate, what do you think the ratio would be? The length to this length. What's your guess? And then the width to that width. So if you estimated them, what do you think? Got a guess? Anybody guess the ratio is 3 to 1? What does that mean? It means this dimension, DC, is to D prime C prime. It's 3 times longer. Or AD over A prime D prime, DC over D prime C prime, and CB over C prime D prime. All and there's a missed one. BA to B prime A prime. They all have the exact same ratio, 3 to 1. There's an easy question. What must be true about the angles? Well, we know that they're all equal for two reasons. One, we heard that's what's true about similar figures. Their angles are the same. But we also know they're both rectangles, and rectangles have all right angles. So here's our definition of similar triangles. We had one kind of like this for congruent. Remember that one went, two triangles are congruent if and only if there's a correspondence between their vertices such that their corresponding sides, it was the same all the way up to this. But congruent went on, their corresponding sides and angles are equal, or we said CPCTE. Well, the definition for similar triangles, a lot like that, so that'll make it kind of easy to memorize. Two triangles are similar if and only if there is a correspondence between their vertices such that their corresponding sides are proportional and their corresponding angles are equal. Again, a correspondence between their vertices. This is not a great picture for that. But you'd be able to take this triangle and line it up on top of this so that the shortest sides are over here, the next longest sides are here, and the longest side is there. Looks like this one you'd have to flip to get BA over here on FE. But once we've done that, what can you say about the similar triangles? Angles, what can you say about them? Well, angle A would be equal to angle, which one? Right? Angle E. How about angle B? What do you put that one equal to? Correct, it would be angle F. And angle C, well, the only one remaining is angle D. That's only one part of it. The corresponding angles are equal. How about the corresponding sides? Well, we could set up a ratio, and if we put EF in the denominator of the first ratio, what would we put in the numerator? Now, it's pretty important to try to get them in the right order. I think you know it's this side right here. But how would you name it? BA or AB? Well, since we started at E here and went up to F, we ended up on the vertex of the long side. Then I'm going to do the same here. I'm going to start at A and end up at the vertex of the long side. So it would be AB there. Let's put BC in the numerator of this next one. So we're saying this long side, and I'm starting on the end, the vertex of the shorter side. So when I name DF, the shorter side is here, so I'm going to name that one FD. I'm going to start there. See if, oops, I gave you the last one there already. That was a little bit fast, but CA, it's the medium-sized one. We're going to start on the vertex of the long side. So we're right here. So we would say DE. So you want to be careful the way you name these corresponding sides. Let's do the same on these two triangles. You say, hold it, there's no picture. How do I do that? Well, it's actually easier, because angle R is the first vertex. That's the first angle. Just take the first one over here. So angle R equal to angle M. Angle S then is equal to angle L, and angle T equal to angle N. That makes it easy. How about the sides? Well, if we start with ML on the second one, what would go above it? Just jump over here. It's the first two vertices, or first 2 points here. We can work our way through with the rest of them. There you see ST over LN. Last one may be a little trickier. What's left? TR. If you chose that side, then over here, of course, you would want to choose what? You'd want to choose NM. If you started and said RT, that'd be totally fine. Then you would go MN here. We've chosen TR and NM. Okay, our next slide talks about dilation transformations. We're going to spend a good little bit of time on GSP in one of our class periods working on this, but today we'll just point out some of the vocabulary. What we actually have here are some original images. They're the ones in the black. Triangle and this circle. And then we've enlarged them. The red ones are the enlarged figures. And here it happens to be smaller. So it's different sizes. O is what we call the center of the dilation. So we pick a point, draw a straight line through one vertex of it, and just continue it out here. We do that with all three vertices. And then when you connect those, you get an enlargement. Well, how much larger is it? Well, this is telling us that the image OA is 2.5 times larger than the original OA. So from that center of the dilation, R is the magnitude. So this is how much larger, or how it's changed, I guess would be a better way to say it, or how much larger or smaller it is compared to the original. If you look over at the circle here, the original is the black one. So they drew a line from the center of the dilation to different points. And then once they had those points, they built a circle on there. Now this one's obviously smaller, and it's by a magnitude of 3/10 smaller. As I said, we'll work on this with GSP on another day. So Chapter 10, Lesson 2 works with similar figures and the idea that their corresponding sides are in the same ratio, or another way to say it is their corresponding sides are proportional, and their corresponding angles are equal. The assignments in Gradebook Wizard. I'll try to work through a few of them here with you, answer any questions I think may come up. So here's our first one, and I found this pretty amazing. We've got 3 pyramids at Giza, and they're not just haphazardly thrown out onto the desert floor there. The Egyptians studied the stars, the 3 stars of Orion. And this is pretty amazing. They laid out their pyramids in the same arrangement as the stars from the constellation Orion. That's kind of cool. So now, since the two triangles, the one that was here and the one that's over here, are similar, what can you conclude about their angles and sides? He's asking you to work with that definition of similarity. Write out the words there. In this one, they're talking about, these are plane tables, they're called, and it's kind of interesting how they created maps back in the day. So they had this plane table and they sighted on 2 points here. So they drew a line on their plane table that would continue on to that point, D, and another one that along the plane table had a line and would continue to E. So they'd sight it in with this surveyor's scope. Then they would take the plane table and they'd move it over, and then they'd sight back into D and E. Where those intersected, they put points. Now if they do that enough times, they would be able to take the physical features of the ground and bring them down to a smaller size of this plane table and end up with a map. Kind of ingenious. What makes this work? Well, in the process, they start out with a big triangle and they end up with another triangle down here, which we're told is similar to the original. Then they have another triangle and a smaller one here on the plane table that is similar again, and that's a given. So you copy the equations below and then complete them. So you keep in mind those two are similar, those two are similar, and now you have a bunch of equations. So again, you know what's true about angles of similar triangles. Get them in the right order. So DAC, and now we're looking at the smaller triangle, FBC. So watch how you label those. You're going to have the same issue with the ratio of the corresponding sides. AD is to, now you wouldn't say FB, you'd want to go BF in the same direction. I'll show you this manipulative in class here. It's pretty ingenious. It's a linkage created. And what he did is, you see that OA, this is to OC. So he made the length such that that ratio was equal to OC over OE all the way up here. And then that ratio was the same as OE to OG. That's all in our given right here. Now they want you to use the means extremes to figure out OE and OG, these, with the givens that OA is 1 and OC is 2. So now you're not going to use all three at once. You'd use 2 of them at first, plug in to calculate one of them, and then once you have that, then you can use either these two, or you can use the first one and the third one to get the other answer. It's kind of interesting here, and you'll see it in class, that this whole gizmo here, this whole linkage, can be bent and twisted. It moves around. But we're told here that as the linkage changes shapes, the following 3 triangles are always similar. OAB, OCD, and OEF always remain similar. Well, because of that, they're asking a question, what can you conclude about these angles? So the angles down here. And with an explanation, tell why. And then kind of an out there question, what does this whole linkage do to angle AOG? Think about your answer to number 10. I think that'll make it easier. So here we have some billboards. They come in 2 sizes. Here's one, here's another. Do they look similar to you? Maybe, kind of the same shape. But we're told in number 12 they're almost similar, but not quite. You'd have to figure out how to show why they're not quite similar. Remember, the definition of similar figures is their corresponding sides are proportional. The corresponding sides would have the same ratio. Then they're asking you to take it another step. Change the 23 here so that they are proportional. Set up a proportion, put an x in there and figure out what it would have to be for them to be similar. And then again, same idea for 5. Change the 5. What would it take? Okay, we get into some dilations. So we've got A prime, B prime, C prime is the dilation image. So this is the image of ABC. So it's obviously a little bit smaller. Working on some vocabulary here. They asked you about point P. Now you have to actually measure in your book the lengths of all 6 sides of these. So you'll take some time, measure that out carefully. In centimeters they want. So it looks like if you're watching this before you do it, you're going to get a little assist there. And now they want to have you take a look at them, compare them. How do the sides compare? What is the magnitude of transformation? Look back in the lesson. What does that mean? What is the magnitude of transformation? How are these points, this one, and this one, related to the segments? So how is B prime related to BP? And so on. Alright, here we go again. All the quadrilaterals are rectangles. And we're told that ABCD, the entire rectangle, is similar to EFGD. Now when you see that, you ought to think this lesson, what's true? Well, if they're similar, their corresponding angles are equal, which we knew because they were rectangles, but their corresponding sides are proportional. So keep that in mind. I have the word index ratio here to remind you, I'm comparing the larger to the smaller here, perhaps. So now they say AD is to ED. AD is to ED. So I'm right. The index ratio, sorry, somebody at the door there. The index ratio is comparing the larger to the smaller, and they want you to give reasons here. After you've done that, move on to 21. How do we get from there to there? We need an explanation. And then what can you conclude about the 2 rectangles? And what can you conclude about 2 others here? A, E, F, H, and F, G, C, I. Let's take a look, think about those, and explain those 2. We have a proof. This one's a proof where you just take each of the steps here and figure out why I can make each of those statements. No real assist on that one. This one's going to be a sticky credit optional one, so I'm not going to go into detail on this one. They do talk about ratios. They've got them in decimals. Notice approximate. And then there's a magnitude, how much larger or smaller. Then they're going to ask you to calculate some dimensions. Okay, here's another one. I can't remember if this is sticky credit or not, but it's interesting. The paper that you use in 8.5 by 11, or maybe you've seen A3 and A4 sizes, they don't start out that size. They start out as very, very large sheets of paper. And then they cut them up, but they cut them in an intelligent way. They keep cutting them in half. So what do they say here? It's set up so that a sheet of a given size can be cut in half to produce 2 sheets of the next size that are similar to it. In other words, when you cut this, these 2 are similar to the original one. Now notice they are flipped, right? This one is long way there. This one has the long way the other dimension. To within a millimeter. So size A0 has a length of 1188 millimeters. We don't know what this width is here, but they're going to ask you to try to figure that out. So refer to the figures to write a proportion for the corresponding dimensions of sizes A0 and A1. Solve it to find x. Little question they're throwing in there. When you look at your proportion, it'll become clear on 42. Now once you have dimensions, you can calculate the area. They're rectangles. Think about how you find the area of a rectangle. The width of A2. So now we're looking for this number right here, which you can use your previous work to figure that out. When the system of papers was established, the dimensions were rounded off. Refer to the figures above to write a proportion for the corresponding dimensions of two successive sizes. So you're putting in some rounded off numbers there. Picture frame. Here's our next problem. So it's 28 by 20. It's labeled. Now let's see. That's actually the picture is 28 by 20. And they've got a frame around it. And that frame is constant. It's a certain length. I wish they'd given us a number, would have made it easier, but we write a proportion based on the assumption that the outer edge of the frame has the same shape as the picture. Well, that's another way of saying that the whole frame is similar to the actual picture inside of it. So keep that in mind. Now you're looking for a proportion for W. Solve a proportion for W that you created on 48. So I'm using an index ratio here, F over P, and that equals, well, frame. Got to think about that a minute. How long is this? It's not W. It's 28 plus 2W. And then it's over the length of the actual photo, 28. Equals 20 plus 2W over 20. So now I did the other dimension here. Boy, I think I give you the rest of the answers here. Well, if you watched, you're getting lucky, I guess. So now what I'm going to use is the means extremes property here. So what's it going to look like? So we got some algebra. 28 plus 2W. So I guess I started here, multiply by 20. And that has to be equal to 20 plus 2W times 28. Now it's just algebra. Distributive property on these. So you should be able to work that out. Just got to check what's left here. Yeah, I'm going to stop right there and let you figure out the rest.